Hello again. This is Math 2245 coming to you from the College of DuPage, and the title of this lecture is Solving Systems of Equations. As always, please be an attentive learner while watching this video. We start with a very important definition. A matrix, any matrix, it doesn't have to be an augmented matrix, is said to be in reduced row echelon form if it satisfies all four of the following conditions. Number one, if there are any rows of all zeros, then they are at the bottom of the matrix. Number two, if a row does not consist of all zeros, then its first non-zero entry, i.e., the leftmost non-zero entry, is a 1. This is called a leading 1. Number three, if any two successive rows, neither of which consist of all zeros, the leading 1 of the lower row is to the right of the leading 1 of the higher row. And finally, number four, if a column contains a leading 1, then all the other entries of that column are 0. This is called reduced row echelon form. Note that a matrix, and again any matrix, is said to be row echelon form if it satisfies 1 through 3 of the reduced row echelon form definition. Notice from these definitions that a matrix that is in reduced row echelon form is also in row echelon form, while a matrix in row echelon form may or may not be in reduced row echelon form. Let's look at an example. The following matrices are all in row echelon form. And you can see that by checking to see that they do meet all three elements of the definition. But none of these matrices above are in reduced row echelon form. And what presents them are the ones that are showing in red. So for example, here, this 9 would have to have been a 0. And here those two numbers would have had to be a 0. And here the 5 and 9 and as well as the -8 would have had to be zeros to be in reduced row echelon form. In order for these matrices to be in reduced row echelon form, all of those would have had to be 0. Notice that we didn't highlight the entries above the 1 in the 5th column of the 3rd matrix because that 1 is not a leading 1. So we don't need the numbers above it to be 0 in order for the matrix to be in reduced row echelon form. Now these are all in reduced row echelon form because every time you have a 1, there's only 1 in each column. Now here there isn't a 1, and so that's different. Now in the second matrix, in the first row, they're all zeros. That means this is vacuously fulfilled. So that matrix is reduced echelon form, and the fact that it doesn't have any non-zero entries doesn't change the fact that it satisfies the condition. Also, in the second matrix of the second row, notice that the last column does not have zeros above the 1 in that column. This is perfectly acceptable since the 1 in that column is not a leading 1 for the 4th row. Notice that from examples 1 and 2, the only real difference between row echelon form and reduced row echelon form is the matrix in row echelon form is only required to have zeros below a leading 1, while a matrix in reduced row echelon form must have zeros both above and below any leading 1. So let's start thinking about how to use linear algebra techniques to solve these systems of equations. The process is actually quite simple. To solve a system of equations, we will first write down the augmented matrix for the system. And then we will use elementary row operations to reduce the augmented matrix to either row echelon form in which we can solve it, or to reduced row echelon form. Any further work that we'll need to do will depend on where we stop. If we go all the way to reduced row echelon form, then in many cases we don't need to do any more work to get the solution. And in those times where we do need to do more work, generally we'll not need to do much more work. Reducing the augmented matrix to reduced row echelon form is called the Gauss-Jordan elimination. If we stop at row echelon form, we will have a little more work to do in order to get the solution, but it's fairly simple arithmetic. Reducing the augmented matrix to row echelon form and then stopping is called Gaussian elimination. So we have Gauss-Jordan elimination and Gaussian elimination, two different things. Let's do an example, example 3. We're going to use both Gauss elimination and Gauss-Jordan elimination to solve the following system of equations. So here is the system. You should pause and give this a try yourself. And we'll discuss and see how you did. Let's see how you did. Well, first we put it in the augmented matrix, and then we're going to start using row operations to get this into either row echelon form or reduced row echelon form. Okay, so we're going to look at this, and rather than doing arithmetic, what we're going to do is we're going to start by switching rows. Remember, that is one of the elementary row operations. So we're going to switch rows 1 and 2, and that's what we do in this first step. So we switch rows 1 and 2. Now we have a 1 where we want to have it. We also have a 1 here where we want to have it. Now we have to begin eliminating this -2 and and 3. -2 and 3, we want to make those into 0 using row operations. Okay, so if we take row 2 and add twice row 1 to it and replace that with row 2, we get this. And if we take row 3 and subtract -3 times row 1, that becomes the new row 3, and you see we have done this. And now we have 1, 0, 0. Sometimes this is called pivoting. The next thing we're going to work on is getting this to be a 1. And the way we get that to be a 1 is by multiplying all the way through, again, a row operation by 1/5, and that becomes the new row 2. And then what we need to do to get this into row echelon form is we need to eliminate the -6. So what we're going to do is we're going to take row 3 plus 6 times row 2, and that will give us this 0, and that's what we want. So now you see we've got 1 and then zeros. We've got the 1 and zeros. So now we have to focus on the -2. Now in this case, what we're really going to have to do is just multiply all the way through by -1/2 row 3, and that gives us these 1s, and now this is in row echelon form. And we can solve it once we're in this form. This is Gaussian elimination. So we know that this variable is 2. We can plug this, well, let's just look at what we're going to do. So whenever we take this, this augmented matrix, we really have this. That means x3 is 2. x2 plus x3 is 6, but since x3 was 2, that means x2 is 4. And then we use those values in the first equation, and this is called back substitution, to determine that x1 is -1. Again, this is called back substitution. Now, suppose we wanted to continue working and put this in reduced row echelon form. Well, we would have to eliminate this 2, and we would have to eliminate both the 3 and the 1. And we do that in turn by taking row 1 minus 3 times row 3, and that ends up giving us this, and 2 minus row 3 ends up giving us this. So that becomes the new row 2. And so what we have then is we now have this almost where we want it. We still need to get a 0 here, and we get that by taking row 1 minus 2 times row 2, and this becomes the new row 1. And now we have this in reduced row echelon form, and we can read off that x1 is minus 1, x2 is 4, and x3 is 2 directly from this thing. So you see this works as we suggested that it would, that you end up being able to read these off very quickly if you put it in Gaussian form. Now, before we do our next example, we want to introduce a fact. So there are many paths you can do a problem, and the path will affect the row echelon form of the matrix, but it's not true for the reduced row echelon form. We'll always get the same if we go there. And if we know ahead of time we're going for reduced row echelon from matrix, we might take a different path than one we did before. And so again, you want to focus on the goal, not on what your specific steps. Let's do another example. Now here you have 3 equations and 3 unknowns. So please pause and give this a go. Let's see how you did. Okay, so here's the augmented matrix you should have started with. And what we're going to do is we're going to work to put it in row echelon form. So we do these steps. Get first this, then we multiply row 2 by minus 1, and we get this. Now we still have more work to do because we need to get this to be 0 and get this to be 1. These are the steps we use to do that. To get this to be 0, we do this step, and to get that to be 1, we do this step. Now, if you look at this, you might say, okay, so that's fine, but what does this really say? Well, let's think about what this matrix looks like when we look at the equations. We have all of this. Now, that's okay, except for the last one, and the last one says that 0 equals 1. That can't be, and that means that the official answer is there is no solution to this equation. Let's look at another one, 3 equation and 3 unknowns, but this time we're going to be having a minus 7 here. And please notice that this is exactly the same as what we solved before except for the minus 7. Give it a go. Let's see how you did. Okay, well, when we do that, we can get very much to where we were, except at the last step we end up with zeros across the entire bottom. That's going to mean that's going to be a free variable. And in fact, what we have then is we have x1 plus x3 is equal to minus 4, and x2 minus x3 is minus 1. Now that means that x3 is a free variable. So x1 is equal to minus 4 minus x3, and x2 is equal to minus 1 plus x3. If we call the x3 a parameter t, we get an infinite number of solutions. Now to this point, we work with nothing but systems with the same number of equations and unknowns, but let's do a couple of examples where that isn't the case. And so here we're solving 3 equations, and we have 2 unknowns, x1 and x2. Please give it a go. Let's see how you did. Okay, so what you should have done when you work through this is you will get this kind of expression. That means that x3 in this case is a free variable. It's not really there, but this tells you that x2 is 1/4, and we can plug that in doing back substitution, and we find that x1 is equal to 3. So the solutions are 3 and minus 1/4. Now we're going to look at another one where again they don't equal. We have 3 equations, but we have 5 unknowns. Go ahead and give it a go. Let's see how you did. Now first we know that we're guaranteed to have infinitely many solutions since they've got more unknowns than equations. So here's the augmented matrix for this system. And we'll do row operations. You can see the row operations that we do here. And we get it down to this step, and we're now in row echelon form. Everything below the ones is zeros. Okay, so now what we're going to do is we're going to take advantage of the fact that several of the rows simplify our work. And so what we're going to do is we're going to work backwards to find the solution. And so we do some more, and we end up here with this. So here's the remaining work. So we have this value. Now, what we know is that this tells us that x2 is minus 23 over 15. Here we have what is x3 in terms of x4 and x5, and here is this one in terms of that. So when we define these to be s and t, we're going to get that x1 is this expression in terms of s and t. X2 was minus 23 over 15. X3 is this one. X4 is t. And x5 is s, where those are any numbers. Again, this is an infinite number of solutions. Now, there's one more topic that we want to discuss before we close off this particular lecture, and that is, suppose you have a system of n linear equations in m unknowns, but they're of this form, and that's all equal to 0. We call this a homogeneous system. The one characteristic that defines a homogeneous system is the fact that all the equations are set equal to 0. Now, it should be clear to you that if all of these x's are zeros, that is going to be a solution. In other words, with a homogeneous solution, we are guaranteed to have at least one solution. That means that theorem 1 from the previous section can be reduced to the following for homogeneous systems. Given a homogeneous system of n equations and m unknowns, there will be one of only two possibilities for solution to the system. There will be exactly one solution where everything is 0, or there will be infinitely many non-zero solutions. Note that when we say non-zero solution in the above fact, we mean that at least one of the x's in the solution will not be 0. It is completely possible that some of them will still be 0, but at least one will not be 0 in the non-zero solution. We can also make a further reduction from the previous section. We assume there are more unknowns than equations. Given a homogeneous system of n linear equations in m unknowns, if m, the number of unknowns, is bigger than the number of equations, then there will be infinitely many solutions to the system. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself, because self-care is important, and of each other, because we're all in this together. God bless you all.